So, when you think about a particle collider like the Large Hadron Collider, you probably picture these two little dots, smashing together and creating this big burst of energy. But what if I told you that what's actually colliding is something way, way more complicated? That every single one of those particles is surrounded by this shimmering, almost ghost-like cloud of other particles? Well, today we're going to dive right into that beautiful chaos and figure out how physicists actually make sense of it all.
All right, so here's our game plan. First, we'll see why smashing protons is just so darn difficult. Then, we're going to step back and build a simpler analogy using electrons, which will lead us straight into this bizarre idea of a particle's hidden quantum cloud. From there, we'll watch how that cloud can become real during a collision, and finally, we'll bring it all back to the messy real world of protons.
Okay, first things first. We have to get our heads around the central problem here. In the world of high-energy physics, you quickly learn that not all particles are the same. Smashing some of them together is, believe it or not, pretty straightforward. But smashing protons, that is a whole different ballgame. It's one of the toughest challenges physicists have to deal with.
And here's exactly why. Over on the left, you've got the electron. It's a fundamental particle. As far as we know, it's just a single, indivisible point. It's clean, it's simple. But then, on the right, you have the proton. The proton is a hadron, which is a fancy way of saying it's a messy, complicated bundle of other particles, quarks and gluons, all just swirling around in there. Colliding electrons is like clapping your hands. Colliding protons is like smashing two beehives together and trying to figure out which bee came from which hive.
So, to get a handle on this proton mess, we're going to do what physicists do best. We're going to take a step back and build a simpler analogy. Instead of thinking about the super complex, strong force that holds protons together, we're going to look at the much cleaner, much simpler world of a single electron and its electromagnetic field.
Now this is where things get really cool, because this visualizes a deep truth about our universe. See, when an electron is just sitting there, it's surrounded by this nice, simple, symmetric electric field. But, and here's the crazy part, as you accelerate it close to the speed of light, that field gets squashed. It flattens into this pancake shape. And this squashed-up field of energy starts to act exactly like a cloud of light particles, photons, that are all traveling right along with the electron.
And here's the real kicker. This cloud isn't just some neat little analogy. It's actually a window into what a particle truly is according to quantum field theory. A physical particle, one out there in the real world, is never truly alone. It's always interacting with the fields that surround it.
Okay, I know this equation looks a bit intimidating, but stick with me, because the idea behind it is actually beautiful. Just think of it like a recipe for a physical electron, the kind that actually exists. What it's telling us is that a real electron is a quantum mixture of possibilities. It's partly a bare electron all by itself, partly an electron with a photon tagging along, partly an electron with two photons, and so on, forever. This cloud of possibilities is what the particle we observe is actually made of.
So you might be asking, where do all these extra photons in the cloud come from? Well, they come from something called quantum fluctuations. Thanks to a little quirk of physics called the uncertainty principle, these virtual particles can literally pop into existence out of empty space for the tiniest fraction of a second, borrowing a bit of energy before they vanish again. It's not a bug, it's a fundamental feature of reality.
Okay, now for the main event. So far, this cloud is just this shimmering halo of virtual possibilities. But what happens when you introduce the sheer violence of a high-energy collision into the mix? Well, that's when the virtual can become very, very real.
And this really gets us to the heart of the matter. If a particle isn't just a single point, but this whole complex, fluctuating cloud, what are you actually hitting when you smash something into it? This lays it out perfectly. The collision delivers this massive jolt of energy that just shatters the cloud's delicate quantum state. It's like a shockwave. And that jolt can hit one of those fleeting virtual photons so hard that it gets blasted with enough energy to become a real independent particle. It's no longer just a possibility. It's been liberated. It's knocked free from the cloud and flies off as something our detectors can actually see.
Physicists have a name for this, of course. They call it initial state radiation, or ISR. And it's absolutely critical, because it means that even before the two main particles have their big collision, they've already shed some of their energy by radiating away these real particles from their virtual clouds. If you don't account for this lost energy, every single one of your calculations is going to be wrong.
All right, it's time to connect the dots. We can take everything we just learned from our nice, clean electron analogy and finally apply it back to the original problem, that messy, chaotic collision of two protons.
And the source material we're pulling from really puts this into perspective. For electrons and their electromagnetic force, that's QED, calculating this radiation stuff is what they call a straightforward exercise. But for protons and the strong force, that's QCD, the problem is fundamentally different. You're not just dealing with photons being radiated, you're dealing with a cloud of virtual quarks and gluons, all tangled up in a way you just can't calculate from scratch.
So that leads to the million-dollar question, right? If the inside of a proton is this impossibly complex, non-calculable mess, how in the world can scientists at the LHC predict the results of their collisions with such mind-boggling accuracy?
Well, they use this incredibly powerful idea called the factorization framework. It is a truly brilliant move that lets them split the problem into two distinct pieces. One piece is all the messy stuff inside the proton, the structure we can't calculate, but that we can measure in other experiments. The other piece is the actual high-energy collision between two of the tiny things inside the protons, which, it turns out, is clean and calculable. It allows them to literally factor out the chaos, giving them this reliable bridge between the messy reality of an experiment and the clean predictions of our theories.
You see, this framework doesn't just make the math possible. It lets us isolate the universe's most fundamental interactions from all the complexity that surrounds them. It's just a stunning testament to human ingenuity, allowing us to peer right into the heart of matter. And it really makes you wonder, in all that chaos we see around us, what other simple, elegant, and hidden realities are just sitting there, waiting for us to find the right way to look at them.